one of the things that I felt was important was to somehow let the genie out of the bottle. That where does science come from? How does it just happen? Is there some brilliant person in a room that sits there quietly and, oh, you start studying this thing? No. And so we wanted to kind of crack open this notion of how do we get to scientific concepts and ideas, and then how do we pursue them a little bit, just as a kind of a generic kind of preparation in the scientific career. And I start with the ice axe that Clément gave me. This is the ice axe, and on it says Bonne Aventure. And that really was a very important little message from Clément, because it really synthesized so much of what drives me, is that I'm often looking for something that will be an engaging, memorable experience. Clearly, the scientific adventure is quite distinct from the mountain climbing adventure, but they share a certain passion, and that you will never get to the top of a mountain without being really motivated, without having done your preparation, and being absolutely dedicated to the completion. And similarly, in science, you will never get to the top of the scientific mountain without having your full engagement of the gray area and the conscious mind. I'll never forget the first, my undergraduate thesis. I woke up at 3 in the morning with the solution to the nonlinear wave equation and just wrote it down, and then went back to sleep. And I cannot really take credit for the solution. I don't know where it came from, but that reflected the full engagement. And so when I say bonne aventure, I mean that you need to be really into it. So if you find you're just kind of going through the paces, you didn't commit entirely, then look at it again and say, okay, if I'm going to be doing something cool, I have to be fully there. The other thing that I will emphasize through the talk, and you probably can't read all these names, is that it is a team effort. Even those people who consider themselves to be solo operations are walking specifically on the results of others. We all in science are learning from everyone else. You can look at your neighbor and you will someday use their results as well. So don't ever think of this as a solo experience. This is something which we do as a community, whether you recognize it or not. And the more quickly you recognize that, then events like this, where you can start to talk to people about the nuances of what they've written, really can be fundamental experiences. And then building a team of people who you can work with. As I say, when you get older, this becomes a lot, it just happens. But I wanted to talk to you about a few of the people who have been quite influential in my life in terms of their concepts of how to do science. So Ignacio Rodriguez Iturbe, who is at Princeton now, I guess, at MIT for quite a long time, he said, always be ready with 3 questions just in case God walks into your office. And at first it sounds like what a silly thing, but in fact the point is very clear, and that is that if you ask, you have to have in mind things that you really care about. You're not going to ask God, am I going to flip a coin, be heads or tails? No. You have an opportunity to ask the hard question. So you have these questions brewing in your mind always that you've been thinking about and looking around the world and saying, now that's one I would love to be able to get an answer to. It is the actual process of developing these questions which is fundamental. As anyone knows, a well-asked question is almost as good as a solution, because it will drive you in a very important direction. So I thought that Ignacio's point was very good. My brother Harry is a medical researcher in Tufts University, and I thought that his ideas were horrible in terms of not being humble. I mean, my God, only work on problems that can change the world. Oh, and only work on problems that you are uniquely qualified to address. And then the last one, have fun. And this having fun, this is Olivier Beur and Tanguy. And so I did learn from the French a little bit about having fun in the field. And I will say that the displacement of conversations in the morning over food, they would only take about 2 hours to get our lunch plans basically made. But we still got the science done. So on that, how many papers came out of that experiment? Probably 3 or 4 papers. But my brother Harry's point is that it does matter if you choose an important problem. You can choose little isolated problems that you might take a fascination with, but no one else cares. Life is in fact short, and the amount of money, resources, and time to explore critical problems is finite. So if you're going to make a difference, you need to be the person who says, this is important, okay? Now, in terms of choosing problems that you're uniquely suited to address, this is really a very strong statement of it, but I want to take it on the flip side, and that is that many people say, I want to solve the hunger problem. And so, here I go. Well, that's not a well-posed problem, right? And so you have to think about and understand who you are and what your strengths are and what your weaknesses. And I have plenty of weaknesses. I can't spell very well. You'll see some typos in the slides, I'm sure. I had to convince you that they're there. So we all build, and that's part of this team building. You know yourself, so you know what you bring to the team. You can have confidence of that. And you also know where you need to seek help and need to have a complementary thing. And so if I were to, even though I got lucky at 3 in the morning once, I'm not going to build my career on solving differential equations. There are guys who are better at that than me. There are people who are much more skilled. I go to those people when it gets desperate. Maybe I look at Eve. I'll say, hey, Eve, hey, come on, help me out. So know what you're good at. But in the end, this having fun is not trivial. Because if you are not fully engaged, you cannot remain engaged for many years if you're not enjoying the process. It will get old. You will burn out. You'll be kind of one of the people who is not having a good experience. Well, I'm supposed to tell you how I think about doing science. And this is a rather strange question because you don't really think about it, many of us. But when I did think about it, this is my recipe. And I call it WUMPT, which is not a very lovely word. But the first thing that start off with is I want 5 wows a day. So I want to look around and say, hey, the acoustics of this room are really great, and yet it has hard surfaces. I wonder what's behind those little slots. Are those slots the size of a wavelength of sound? Huh. So I kind of look around and each day try to identify at least 5 things that I just kind of I wonder about. Now, of those, there's is it unknown? Now, it's often that I don't know, which is okay. It's nice to learn. But there's nothing interesting scientifically about me learning something. If you're going to actually take on a scientific problem, it has to be unknown to other people too. The third piece is, does it matter? Remember I talked about my brother Harry's things that can change the world. Life is short, so about 1 out of 10 will survive the does it matter test. Who gives a darn if John Selker understands the acoustics of this room? And then this is not trivial as well. Is there the actual potential for advancement? So I might say that world hunger, no one knows how to solve it. Does it matter? Oh my God, everyone's hungry. Or not everyone, but a lot of people are hungry. Certainly not enough brie out there. But in any case, but is there an opportunity for advancement, where I can see a new way to have cows, come up with camembert immediately? And if there isn't an opportunity for such, then that cuts out again. 9 out of 10 are gone. And then finally, when I've identified something that's going to be fun, and the column experiments that we'll be playing with over the next week or so are exactly an example of this, then we have to form a team. Because generally speaking, the problems that we're working on in our field, in hydrogeology, in the critical zone, are multidisciplinary with many central players, and we cannot be on top of 10 different fields of study. Plant roots, soil structure, microbial community, et cetera, et cetera, et cetera. You need to bring in people who can work with you. So form a team. So I figure out of about 2,000 wanderings a year, I end up working with about 15 teams, as you saw the first slide. So now, I think the key message, if I had to take one thing from this slide, is the first one. And that is, I think that it is a matter of practice. So to come up with interesting questions, you have to be practicing asking questions. So look around your world and try to ask questions and just get into that rhythm. And then only very few, 1 in 1,000, will be really something you'll follow up on. But you do need to sit there and ask questions. If you just look at the literature and say, oh, so-and-so got to this point, I'll go to the next step, that's probably going to be a not very exciting research problem. So I want to give you an example of a WUMPT so that you can make it slightly concrete. This poor little frog is sitting in the rain. You can see his leaf has become heavy, so he's now holding up water and the leaf. And the question we have is canopy interception. So I was on a PhD committee, and they were taking trees, cutting them down, hanging them by a string, spraying with water, weighing the trees to see how much water, dead trees, how much water they would hold, but then that was a very short-term experiment. It didn't seem satisfying. And so it was surprising to me that it was unknown how to do real-time observation of canopy interception in an efficient way. Does it matter? Yes, I think it matters very much to water supply. And in particular, looking at Canada, you can see that the pine trees are dying in much of the western United States and western Canada. This is a complete canopy replacement. When we think about the fact that the canopy intercepts a quarter of the rainfall, and of course, of that 3/4 that gets through, much of it then goes to evapotranspiration. So the amount of percolation into the aquifer that drives river flow is a tiny fraction. So if you change the interception, you can change if you change the canopy, you can change the interception by a factor of 2, which could make a vast difference in the water supply for the western United States at least. So were there potential for advancement? I think we'll see there were. And then we put together a little team, including my brother. You'll see him there. So the first idea was we would take quartz rods that are non-expansive, so they have zero thermal expansion coefficient. And we'll put on these little tiny displacement sensors that are potentiometers. We can measure a micron. We'll put 3 of them around a tree so we can subtract out the wind effects. And we'll look at the compression of the tree stem to give us the amount of water that was held. So here we are. Here's a tree. And actually, you can see some calibration weights. So we basically weight the tree with a known amount of weight. We then calibrate it for its spring constant. Hooke's law is quite linear. And so we can actually get resolution. Here we are putting on, was this 40 kilos? 40 kilos, 20 kilos, and then doing a ramping. We can see about 5 kilos in a pretty substantial tree, which is cool. We can measure down to, as you can see, on the order of a micron. This is doing the same experiment in Ghana. Here we're calibrating our tree, and then the village there. And here was a rainfall event. I've never liked the fact that they plotted the interception as downward, but it rained here, interception, then this was the evaporation off the tree. It took about 5-7 hours to evaporate out that water. So we could actually watch canopy interception in real time, which was really cool. And this was very important for calibrating our satellite imagery to understand the storage of water, because when the water gets stored in the canopy, it looks like soil water. So it was an important way to separate these things out. But this was painful. We were the first people to import heating blankets into Ghana, as far as we know. We did decide to heat the whole tree, et cetera, et cetera. It was a pain, but we got it done after a couple of years. So then I thought, well, maybe there's an easier way to do this. And everyone's cell phone now has a little accelerometer in it. Well, wouldn't it be cool if we just nailed an accelerometer into a tree and we watch the tree oscillate? And then we know that it has a constant spring coefficient, but as the mass increases, just like when you're practicing piano, then your metronome changes its speed. So basically what we do, we put the accelerometer, we watch in time, do a Fourier series, then we calculate the Young's modulus, and then we can look at the changing mass in time. Again, here calibrating with a 70 kilo lump of stainless steel in my backyard. This is my little oak tree. When it leafed out, the mass increased by 240%. So when those trees go from dormant to fully leafed out and pumping water around, the change in mass was phenomenal. So you can see the frequency shift here, which is indicative of the, with constant spring, the mass. Okay, so that's just kind of the WUMPT example, and we had a lovely team that worked on that, doing the Fourier analysis, et cetera, et cetera. That works for me. Ignacio, questions for God, works for him. My brother Harry, what are you absolutely best at? Excellent point, works for him. My feeling is that you have to be true to your own goals and your character. And so each of you has to kind of look inside and say, how do I like to operate in this world? What are the ways, some people are less risk averse and some people are more risk averse. And so, you have to kind of find that balance, where you're going to be happy, where you're going to be able to put your creative, investment in. But fundamentally, I think that science comes from seeking with passion and leveraging your personal skills. And so, should you feel that passion not there, then think about how to adjust your scientific endeavor so that you are interested. You cannot do great science without being fully invested. Okay? So now I want to just talk about a few other kind of pieces of exploration. And so innovative tools, from Lavoisier, et cetera, on, people who had better thermometers were able to make transformative discoveries about chemistry or other processes, for example. And then we have this amazing situation with transformative technology at this point, where we can bring people together and have these non-traditional laboratories where they're more collaborative. And then looking at social structures as a vehicle for advancement. I'm sure you've all heard about citizen scientists, but I think that it goes far beyond citizen science, and so I'm going to try to give you a little example of each of these sorts of approaches. I'm going to go through the social structures one has a few too many slides in it, so we'll kind of go quickly. We can come back to them if you have any questions about those. So the first thing that I worked on in the sense of a transformative measurement technology, I was challenged by the National Science Foundation of the United States and the community. They said, John, we want to have an instrumentation program. And so I said, well, great, but what instrumentation? And then we flailed around for several years, and finally I said, no, we're never going to make progress if we just say we're going to do technology. We had to have something specifically. We had to hit, as we say in baseball terms, we had to hit one ball out of the park. And then we will get the credibility that actual hydrologists can do something interesting with measurements. To this point, most of the US hydrology community just buys instrumentation off the shelf, plugs it in new ways, and puts it into the place. But we have not frequently made transformative measurement techniques available. So let's use light. So the cool thing about light is it interacts with matter in many interesting ways. And so if we inject at a particular wavelength, there are side bands that come back scattering. And some of those side bands come back, and with temperature, they shift their position. So those would be the Brion backscatter. Okay? And then some of these side bands change their amplitude, and that would be Raman backscatter. And so if we have a fiber optic and we send light down it and we listen for the backscatter, we're going to get these two peaks back. And by calculating the ratio of them, as that changes, I know that the temperature has changed. So I didn't come up with this. There's companies that make these instruments. They were used a lot in oil and gas, but they hadn't been used in environmental monitoring to any significant degree. So these are my kids now, 25 and 22, slightly a couple of years ago. Nick van de Giesen going in the mighty Maesbeek River, which you can lay face down and not die. It's a small river. But we put our cable down the river, and so we have about 700 meters of cable represented here. We can take a measurement every 25 centimeters of temperature. Our measurements are accurate to 1/100th of a degree C, well, say 2/100ths of a degree C if you're calibrating them. So what we have here then is space in this dimension, temperature is in the color bar, and then time is going down. So 1 day, 2 days, 3 days, 4 days, 5 days, etc. And what you see, of course, it gets warm in the day, cold at night, warm, But the interesting thing happens right here, where it was very warm, but then going downstream, it got cold. Okay. And the interesting thing here, at night it was very cold, going downstream it warmed up. So what we have then are groundwater inflows. Now in our mighty Maesbeek River, a small groundwater inflow can make quite an impact. And so we can actually see and calculate, given that we had a weir down here and we had zero flow there, we can actually calculate the contribution of each of those groundwater inflows and look at their dynamics in time as that system drained over the season. So this provided a relatively new view of stream dynamics to be able to see exactly where and how much water came at each location. Then we can take that same idea to a much larger river, in this case the Walla Walla River, which is one of the key breeding areas for salmon in the Pacific Northwest. So here's Washington State, Oregon State, and right on the line. So that's just, Canada's right here. So our good friends in Canada, we should say. And what we can do here is by watching the dynamics of temperature, where groundwater comes in, it cooled it. During the summer, it actually cools it both day and night because it's colder. It's the average annual temperature of the groundwater. So we can look at cool places and say, aha, groundwater. And then we can look at compression of the fluctuations, and say, ah, that's hyporheic exchange. That's water going into the groundwater, coming back into the bed, going back out. And here we were actually able to identify each of these groundwater and hyporheic exchange points. And in fact, our prediction of where salmon would be was better based on these data than on all the habitat studies that the biologists had done. So we could actually tell them, no, they're going to be here, 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 and here, because that's where there's nice cool water, and that's where it's stable temperatures. So with just laying a cable, we're able to identify very, very important piece of the habitat of the salmon. Now, this cable can also be used underground. Now, what can we do with this cable underground? Well, here we have Chadi Sade and Chris Gregory pouring sand into this column. It has this fiber optic cable going down there. And at the bottom, we have a garden hose that's perforated that we can adjust the boundary condition with. Just about science, almost everything we do is unfunded. So it's a weird thing, but the grants pay for kind of the bread and butter. But then the real good stuff often comes with just a couple of inspired students, and we kind of whack it with a hammer and off we go. And so keep in mind that don't ever let a good plan get in the way of a great opportunity. Okay? So what are we going to do here? What we're going to do is we're going to wet up this column and then dry it. Now, this cable has a stainless steel jacket around it, so we can run electricity along that jacket and heat it up. Wet sand has a higher thermal heat capacity and a higher thermal conductivity, and so it's much harder to heat. So we expect that where it's wet, there will be less heating, and where it's dry, there'll be more heating. And indeed, that's what we find. So here is the dry sand heated up to about 12 degrees C after about 5 minutes. The wet sand only heated less than half that amount. And so then we can run a calibration curve where we have the area under this curve. And we know that the area will be proportional somehow to the water content. And so we just calculate the area. That gets rid of the noise to a large degree. So we have very small standard deviations. And we're able to get a calibration of water content versus the area under the curve. And so it gives us a really nice range of operability for measuring moisture content. Interestingly, as it turns out, the error on water content as a fraction of the total water content is more or less constant. We can't distinguish very well between the very, very wet end. But our fractional error of about 4% is held here. But we also have a 4% error when it's only 10% wet. So we have 0.4% moisture content resolution. And it turns out, typically, in environmental situations, we're more interested here than here, fortunately, because very rarely does the soil stay very saturated. Now, here we did an experiment. Under a field, we put these fibers in the ground. This farmer had his sprinklers right in the corn, which was great for us because it's going to focus infiltration. And here are the results looking after 3 hours, the green line, and then 9 hours is the red line. So irrigation is going hot and heavy. And then after 15 hours when the irrigation had stopped, this is at 30 centimeters depth, and this is at 60 centimeters depth. So keep in mind, we have approximately 1,000 measurements of moisture content along each of these transects. So in terms of understanding the critical zone and knowing where the water is and how the dynamics work and how deep that water penetrated, et cetera, it's very informative to actually have the data. So I claim that we shouldn't be satisfied by taking data the same old way with a little point sensor. We should actually be using novel techniques. Now, okay, we did this in the soil, but then I had some friends who are atmospheric scientists. They said, hey, can we do this as an atmospheric science approach? So here we have 3 cables, 2, 1, and half a meter height, and we're going to heat the cable again. Now we have next to it a reference cable and the heated cable. If it's windy, then the heated cable cools off. And so the difference in temperature between the 2 cables is a function of the wind speed. Okay, so that's the simple game plan. We have actually 3 cables in total. We have 2 to take out the solar effects because we have a large and a small cable, so we can actually measure the amount of solar heating that happens as well. And these are the types of data you get. This is just the temperature. And this alone was like enough to make the trip worth it. Because what we saw in this little valley, 240 meters across and only about 15 meters of elevation change, there were these fronts between 10 degree and 2 degree air blowing back and forth across this valley. So the stratification, and we had it at each different level, was really impressive. And to be able to see it, how it worked with the landscape. Furthermore, look at the delta T, the difference between the heated cable and the unheated cable. what we have is that when there's high wind speed, delta T is small. When there's low wind speed, it's high. So this is all the low wind speed nighttime. These are high wind speed periods. But let's go ahead and check it against a sonic anemometer. So although I've got about 2,000 points of measurement in my fiber, we can take 2 sonic anemometers and put them next to it and say, how does it line up? So here we have a sonic anemometer at 2 meters height and one at half a meter height. And what we see is that, so this is a half meter height. The dynamics are the DTS has the line and the sonics are the dots. And you can see we really reproduce at those 2 points the sonic data. So it's really exciting that we can actually now see at large scale in space and time the dynamics of wind. And if this video works, oh wow. That is a big if, it turns out. Wow. I've never seen this is a, well, voila. That's interesting. That's the first time I've ever seen that bad. So if anyone wants to stand up in front of the green screen and kind of get videoed, and then you can patch. No. Anyway, what we were supposed to see here was actually watching 2,000 points in space and time of the velocity field. And you can actually see the velocity field dancing, essentially. That each point had these resonances that would speed up and go down, speed up and go down. And that resonant frequency was a function of what time of day and the buoyancy of air. So it's kind of like was, for me, very kind of revolutionary in terms of being able to see the wind structure. And that's actually been fairly interesting to the atmospheric community. As I mentioned earlier, I really think that science is about, it's a collective undertaking. And so it is something that we definitely do together, and it's wonderful to be here with everyone. I'm going to talk a bit about how we do that more specifically. So the first thing I'm going to say is lend a hammer, lend a hand. So the first thing we have to do is be very generous with our techniques and our time. Because by being generous, and I look at Reen, who has trained how many people in Hydras? Maybe a few tens of thousands or something. And so why does Hydras have a huge impact? Because Jurka and Reen went around and said, hey, we're going to help you get this to work for you. So lend a tool and lend your time to make these things happen. The second thing is let's leverage the environment we're in technologically. We can now do things open source. So let's make sure that we open the door, recognizing that we are here to help each other. And then I think I've tried to emphasize doing something important. I want to try to give an example of something that I've found to be very important for me and has gotten me motivated. And then, again, leveraging the web. Danny and I are working on an open source book. And I think that type of activity has to become the norm. So this team building thing was started for me when I was very, very young. This is my first go-kart that we made out of a lawnmower. But the interesting thing is that when I did it, I was very impatient. And so I simply strapped a chair on top of a lawnmower and I was driving around. And my friend Tom said, this is unacceptable. And so between Tom and I, we really got this thing going where we'd actually go about 30 kilometers an hour and had a seatbelt, and it was great. But it would have never happened without Tom. And that has to be a key realization there. So when we're talking about lending things, we have this center called CTEMPS, the Center for Transformative Environmental Monitoring Programs. And that is a National Science Foundation funded center that Scott Tyler and I run. And basically it was the whole thing with the fiber optics. We got it going, but then we said, well, who's going to use this if they don't get training, if they don't have access to the tools? They're very expensive. So we said, NSF, will you help us do this? They buy maybe 10 DTS, and then we can actually get people using it. So we run workshops, and we train people. In this case, we were contacted by folks at the Dead Sea, and we went out and built a little raft, put in the fiber optics, and we could actually watch the dynamics of the interface between the heated surface and the subsurface. And we actually were able to identify that the interface was highly unstable, that the salt, when it would be hypersaline on the top, when it cooled off, it would come down in fingers, and then there'd be crystallization of the salt in those fingers. And so it was a really fun little thing. I would have never been in the Dead Sea if it weren't for the fact that we had the center that people could know, oh, I can get tools, I can get help. And so I think that you never know about the opportunities that you've passed up by not offering your help. The other thing is this idea of how do we bring new technology that requires multiple disciplines to the field. So in specific, how many of you guys have heard of Arduinos? Okay, good number, right? And then maybe cool new sensors like, new pressure sensors and oxygen sensors and these. You've heard of these different sensors technologies, okay? And then you have to think about the power systems and stuff. And then you have to program it all up. Well, even though we know these technologies exist, it's very difficult to implement them individually. It's hard for us to get over the threshold of knowing enough about each of these technologies to make it happen. And so we were cogitating on that. And so I put together a group, and it's called the OPENS Lab, the Openly Published Environmental Sensing Lab. So we have a lab director who actually has a PhD in music, but he did sensing for bands. So all the musical instruments had sensors on them. They all wirelessly communicated and stuff like that. It's really cool. And then we have a bunch of undergraduates actually who are the technicians. And so what happens is visiting scientists, for example, a team from Germany with one professor, 4 PhD students, or 3 PhD students and a technician actually. Anyway, they came to the lab and in 2 weeks they had completely made their prototype system, had it working, and went back to Germany and have had a lot of success with it. So we've had people from Israel, Germany, Taiwan, etc., come to the lab and just kind of get enveloped in the technical kind of team who can then get them over their obstacles. And so we've made a lot of cool technologies, calibration systems for rainfall measurement. Clement has the open sampler, which does gas impermeable sampling, so you can do actual groundwater samples with hopefully with the gases preserved. We have a rainfall isotopic sampler. We have this thing called the evaporometer, which actually catches rainfall and then weighs the loss of rainfall, so you can actually get the evaporation rate. And then this is a subsurface isotopic sampler where you have a porous membrane around a column that you can actually then have segments. These are just a few examples of the types of things that the lab has come up with. Again, what the cool thing is that we don't have to have all these ideas. That people come with ideas, they come with a need for technology, and then we have the 3D printers and stuff like that to make it happen. So think about participating in such a thing, but also if you have a special skill set at some point in your life, you might want to put together a lab that is not just for your own team, that's actually a lab that will bring people together, so community building. And then I want to talk very briefly about this Trans-African Hydrometeorologic Observatory. And this was kind of one of those things where the problem, the interest in the problem finally overwhelmed us, and for better or worse, in terms of how do we identify a problem that will get us motivated. And for us, Louis Pasteur said that good luck will not favor those who haven't prepared their minds. And so the question that we had to ask, my friend Nick Van Diesen and I, is have we prepared ourselves for the African century? So 60% of the arable land that is yet to be exploited is in Africa. And most of the available rainfall that is not being currently exploited is in Africa. And of course, there's a huge population and very low productivity. Have we done our homework? Are we prepared for this? And I claim no. We sit here wringing our hands, wondering what to do, but not sometimes. And it's interesting, I don't know if any of you, probably not. I can barely stand it. You go to a UN meeting and they start talking about Africa. And it's all this highfalutin language and collaboration and blah, 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 blah. And they all leave the room, they go home, and they have their per diem, and they're happy. This is the current model. And it's really scary because we have a huge problem in our hands. Africa, number one, is big. So here we have the United States, all of Western Europe, China, and India somewhere packed in here too. So number one, we see that Africa is big. It's important in that sense. The rainfall is impressive. Here's all of China. Here's where they get more than a meter of rainfall a year. Here is Africa, we get more than a meter of rainfall a year. And this, Madagascar fits right there. So what you see is that the amount of rainfall that's falling in Africa is actually dramatic. But that rainfall is poorly monitored. There are approximately, of the order of 20 to 40 stations through this part of Africa that are actually functioning. In all of Africa, the WMO is having 300 stations report for the entire continent. Most of those are in South Africa, a few in Egypt, a few in in West Africa, but very, very, very poor distribution. It's shocking to see since 1955, they've lost 90% of their reporting stations. What? You know, when cell phone coverage is ubiquitous in Africa, how is that possible? It's like almost, we have self-powered stations. They send their data up. It's 25 cents a month to send all the data from a weather station every hour. Why is this happening? It's a really, really interesting question. It's not only happening just to the meteorologic stations. This is the observations globally of stream flow. And the reporting number of stations going to the GRD data center went from on the order of 7,000 to 1,000 over the past 25 years. So there's globally a huge issue with getting climate data. Again, shocking when you think about the fact. No, this is the world. This is the world. And the GRDC, it's not the only place that stores data, but it is. And this is the plot they put out. I know in the United States we have more stations than this, so I'm not sure why they don't have the US stations, but globally there's been a tremendous loss of accessible data. Now you might say, well, that's why we made satellites, right? Let's just use satellites because they tell us so much. This is our unhappy president, past president. We all know that things are tough. But this is a satellite image of daily rainfall versus what we actually observe in Kenya with 73 stations. The correlation coefficient is about 4%. The R squared is 4%. But good news, the slope's only off by a factor of 5. So that is your current best NASA product. And this is really shocking. And so keep in mind what the CHIRPS program that NASA uses is the word is that it's calibrated based on ground stations. If there are no ground stations, you get lousy data. So they have no ground stations to calibrate to. So it tells, yeah, there's a cloud here, but how much is it raining? Is it raining? So satellite data cannot be used. Again, opportunity for impact, African productivity, the harvest in kilograms per hectare. These blue dots are Africa. And the income per person, this is below 1,000 US dollars. And so what you see is that since over 60% of African activity, economic activity is based on agriculture, this burden of having poor productivity, because we know nothing about when it's going to rain, for example, is putting an incredible weight on the entire culture, many cultures across Africa. So we know that we need to do something. And the funny thing is, if you look at the kind of like, does it make economic sense? The U.S., our weather market's worth about $100 billion a year. So assuming $50 billion a year in Africa is quite conservative. If we put 20,000 stations out, blah, 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 our payback ratio is about 4,000 to 1. If we were to get the value of these. So if we were to put out these $2,000 weather stations with maintenance, we'd still be getting a massive positive benefit out of it. So that it seems that the opportunity is there. Furthermore, people like the African Development Bank are currently investing $660 million in 11 countries to improve their weather observation system. So we know there's big money out there. Now it turns out, we can do the whole job for about 50 million. So it's a bit frustrating that the current donor community actually, we're doing a lot on education to say that they shouldn't use the same models they've been using because they've been failing over and over and over. So anyway, we put together this TOMO thing. We give away
Sorry.
Yeah.
I was just wondering, I mean, you're saying that for a certain amount that's invested, there's a 4,000 ratio payback, but what shape is a payback in? Is this like assuming that there will be a tax or something?
No. It's in terms of, I'm not tracking who gets the money. Yeah. So the point is that the farmers and the people who live in flood-prone areas, and those people will have a positive impact on their life. They will feel a lessened loss and greater productivity, but it's a good point that there's not an economic line between their benefit and running the stations. And that's a really good point, and I will talk about that in just a second. But the good news is, when you got 4,000 to 1, then you can actually make it work. You don't need a big fraction of the resources, you just need some. And so that's our kind of concept. So we've got this website. You can check out the website. We helped the meter group develop this station, which has all these cool properties, lots of nice measurements. It calls in once an hour. We even have a lightning detector on it because it turns out many of the crop damage comes from, and large storms can be tracked by lightning. So it's good to have a lightning sensor on it. We got rid of all the wires and all that stuff. And then in terms of what we've actually done on the ground, this is our current map of station distribution. We've been putting stations out since about 2012. So bulk of them in East Africa and West Africa. We're now putting Mozambique, Zambia, South Africa, Tanzania will be getting about 70 stations. So we're spreading further. But these data, by the way, you can click on any of those little boops and you'll get a little data set. So you can just get those data as you like. The economic aspect, what we do.
Sorry.
We?
I was just wondering, like, how do you decide where to put the weather stations?
Oh, God. That's a good question. How do we decide where to put the weather stations? Well, first off, we have a student who's right now at her desk, right, Amelia, who's right. I look at Nicole because she sits next to Amelia, and Amelia is programming away like a maniac, trying to optimize because we have 12 different parameters, and it turns out people have not taken the time to do multi-objective optimization of location. So it turns out it's a good question. What are you using these data for? So for example, so is rainfall the most important thing, or temperature, or humidity? Well, what we decided to do was use synthetic calculated values. So we're using, like, for example, evapotranspiration. So what we do is we calculate the expected evapotranspiration. We use a reanalysis product to say what the real weather was, and then we take our stations, distribute them, and then interpolate from our planned stations. And then in our interpolation, we say, now how bad was our estimate of evapotranspiration? And so then we say, aha, you can optimize the placement to get a good value of evapotranspiration. So basically, we look at temperature, precipitation, evapotranspiration, and other kind of highly needed quantities, and we then optimize the distribution to get the best values. That said, that's a work in progress. What we often do is we work with the countries, and so we work with the Met offices, and they often have strong feelings. And so what we found the best approach, just as a starting place, we've only put in 500 stations, so we're shooting for 20,000. So a starting place is to say, oh, we want one in every county of your country. So we'll just say, because it turns out counties are often scaled according to the population and the importance. So in the north of Mali, the counties are giant. In the south of Mali, they're smaller. And so you can actually, by putting one in each county to start with, it gives you a starting place. The second thing is we put them in schools, because the school kids love their stations, they look after their stations, and we've had no problems with vandalism in that way. The school teachers actually do the maintenance for us. And so we keep in touch, and then we have little competitions and stuff like that to get this kid. So, yes, we have lots of great ideas about how to optimize our locations ultimately. Right now, we're kind of using some very basic strategies to get out in the field. Okay. So anyway, we give the data away freely to all you guys. So any researcher who wants to put out a publication on Africa, so you can get the whole data set, real time, do cool stuff. We give the data freely to the host governments. Now, we could charge these people. Questions?
Is there any country who would reject putting such?
Any what?
Any country who would have refused to put such stations?
Yes. 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 Next slide. You guys are great. Actually, no. So what basically, we could try to charge people for these things, but our basic objective is that school kids, researchers, and the government should have these data so they can do important stuff. And then who are we going to charge? Companies. So our biggest client is IBM. IBM owns your pocket. Your telephone is probably running the Weather Channel. The Weather Channel is an IBM company. And guess what? They get a lot of money out of you. You don't realize it, but they're actually tracking all sorts of stuff that's kind of, Anyway, so they want to have Africa. They want to have Africa in their pocket as well. And so for them, it's worth many millions of dollars to have just that, to be the conduit for weather data. Great, wonderful. Insurance companies, they want that data too. Lots of people want the data enough so that to pay our small $50 million investment of initially and $1 million a year, no big deal. Okay, so that's how the economic model works. Countries, the negotiation with countries typically takes 3 years. So Uganda took 5 years, Nigeria took 5 years. So what we do is we work with every country and come up with a memorandum of understanding saying, you will allow us to put stations there, we will give you the data free of charge, and we give them a big red button, and if they want to shut us down, they basically hit the button and say, we are out of business. And basically because we see it as a matter of sovereignty, that we're not going to, if someone came into France and said, I'm going to monitor France for you, free of charge. It's like, what are you going to monitor? Everything. And it's like, well, and particularly Corsica, that would be really exciting. Anyway, so anyway, we feel that we have these countries all signed up, and we're very close on a few others, but we feel it absolutely essential to work collaboratively with the countries. Okay, I am going to just zip through these things. We're not going to worry about it. That's the book we're writing. I'm not going to worry about this either. What I want to do is draw this all together because we're running low on time. We have still 15 minutes to talk or more, I think. But so the things that we know that there's incredible opportunities. And so please do not be satisfied to stand by and watch those opportunities sitting on the table and not being, with our community, not taking advantage of them. So WUMPT is I want to emphasize, it's about practice. So don't ever think that some people are creative and some people are not. It's all about practice. You have to practice getting out of the box. And so you have to practice looking around, thinking, then let those, then use the web, explore things, have interesting conversations, practice, 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 practice. And so the cool thing is we get to do it together. And so engage your community in your interesting questions. I think that the simple single disciplinary problems have been addressed to a large degree. The problems we get to solve in our lifetimes are these really complicated problems that require teamwork. So work across disciplines, work with exciting teams. And then I claim dream big. It turns out that of course, if we don't do it, who will? But moreover, when you do dream big and when you do try something exciting, then other people get excited as well. So you have to be a little bit practical. You can't just do everything, but you also have to be a little ambitious, I think. And so think about what could go well. Not how many of you have had conversations with someone who are always saying, well, that might, oh, John, and I love these people to death, but I don't listen to them very much because you have to go forward with optimism, and as my brother Eric, who I didn't talk about, he's actually anyway. He told me long ago. He said, John, have multiple things going. You cannot put all your scientific hopes in one basket. So have multiple things going, and be a little optimistic, and then identify those things which are actually making progress, and then jump with those and keep on expanding your portfolio as you kind of develop your own background so that you can be more effective. But bottom line is move forward, move boldly, and then have a great time. So that's kind of the kickoff to get you guys thinking like at least some scientists think. And I would love to hear your feedback or have any questions. We are in the Democratic Republic of Congo. It is a complicated country to work in. We have 12 stations there. And luckily enough, a Swiss colleague, Johann Six, has been working there for the past decade, has personal relationships with the experiment stations. And so there we went down the Congo River and have placed stations down the Congo River. And then also on Lake Kivu, on the western side of Lake Kivu, that's DRC. And we have a professor who got his PhD recently in Belgium, and he's operating 4 stations there for us. So in fact, we are one of the few groups in the world that has stations in DRC. And we're currently negotiating with Somaliland. We hope to have a set of stations up in Somalia as well. But yeah, DRC is very important. It's also challenging. And many of these places, when we went to Lake Chad, my wife, that was the one place she said I couldn't go because there was live fire on the lake. But we found this guy in the middle of the United States, a guy from China who is a professor, and he just had to study Lake Chad. He went out there and put 5 of our stations up. We put redundant stations there. We put 2 stations at each location because we knew it'd be very hard to get back to there. And so we hopefully will get more reliability that way. But we're trying to go to some very difficult places. We only do it when we can get official government buy-in. And at DRC, we have done the official buy-in by working through the experiment stations and through professors. And we check, hey, do you have authority to do this stuff? Yes, then we go. Ethiopia was a very challenging country as well. It's a very important, Nigeria and Ethiopia, of course, are the two largest countries in population. And so we've just broken through it in both of those countries. We have about 40 stations in Nigeria now operating and about 12 in Ethiopia. But yeah, good question. I mean, it's a big continent. It's going to take some time. Yeah. Voila.
Okay. Now, what are your 3 questions for God?
Oh boy. Well, I'm not. First off, I claim that I'm not Ignacio, so I forgive myself that. What are my 3 questions for God? Good one. That's it. Yeah, I'm really. At this point, I'm really curious about turbulence. And I want to understand how turbulent atmospheres interact with snow. In particular, I believe that snow melt during flooding is a function of the turbulent behavior of the air, and that's a controversial point. And so that's one that I'd like to talk to God about. And then I've been interested recently in the deep Vado zone. In fact, there's going to be a bunch of articles flying back and forth, pointing fingers at each other on this issue. I know I'm dealing with several. And so I've put out, so I'm really interested in how the deep Vado zone works. And it turns out the deep Vado zone has some really special behaviors that have been poorly recognized. So I want to talk to God a little bit about this recirculating zone. In the deep Vado zone, it turns out vapor goes up and liquid goes down. And it's a highly unexpected thing. Are those fluxes significant? Where does the salt end up? Does it end up leaving precipitates at depth? So there's a lot of questions I'd like to speak to him about that. What would be the 3rd question? Well, life? Yeah. Well, I mean, I'm really curious actually about roots. And so I've always wondered, are the roots chasing the water, and what is the exact role of the root fine matter, the fine root tissue? Because there's so many, it's such a massive investment. And from a hydrologic point of view, I think that it's because of limitations on transport, that when you get to high negative pressures, that you have to go chase the water. So my question for God is, are the plant roots absolutely chasing water with those little fine root hairs, or is there another function as well that I've missed? So those are 3 questions. Those aren't the only 3. Yeah.
Thank you very much for having this last thing, because that actually connects to my question. So I'm the picky one here.
Oh, good.
And so when you talked about this accelerometers on the trees,
yes.
I wonder how can you discriminate the effects of the change in mass of the leaves versus the changes in the ground? You never said something.
So the question is, how can you determine the effects of the mass change versus the fact that the soil might become softer? And that's where we have to distinguish between resonant frequency and damping. So the soil, when it can move, it will provide a strong damping. And so we see that many of our signals are damped. But that it should not fundamentally, in my opinion, change the resonant frequency. But this is, trees are fractal-ish, and there's a lot of conversations right now about, well, is there a dominant resonant frequency? We see one. Interestingly, trees, 0.3 hertz. So when you're on the beach here and you're looking at trees, take a look. I claim that most trees are 0.3 hertz. Why is that? That's another question for God. But my first answer for you is that I tend to suspect it's a damping issue, not a resonance issue. Yeah?
There's a slide called Rain Followed by Evaporation, one of the first ones. I don't know if you can go there.
Rain followed by evaporation?
Yes.
What, my slide?
Yeah. At the very start.
Oh dear. Oh dear. Where? It was way too hard. Voila. Voila.
There's a sudden jump
You mean like this?
No, at the start. Oh.
So this is actually increased mass. So this is the rainfall happened here, and it goes whoomp, and then it kind of like bup, 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 bup. Yeah.
But just before there's like an apparent loss of mass. Is that just?
You mean this up here?
Yes.
Up, yeah. Well, there's something here too. So the tricky thing is that when we're doing these analyses, we're strobing all three sensors. And so there's often a phase issue that so the wind is blowing and one sensor is getting smaller, one's getting bigger, and you're strobing them. And the real pain was we couldn't read them all at the same moment. And so what we were finding is there was often like almost a Lissajous pattern where we'd see that we have a repeated overemphasis on one and underemphasis on the other. So my suspicion is that this is just a wind effect that we were preferentially oversampling one of the detectors. I will say this was an extremely difficult experiment. And this experiment, to get this set up and all the bolts in the trees, everything held, and nothing touching anything. So if the quartz rods were protected, if anything touches something, then there's friction and So
Just at the start of the rain, I was wondering.
yeah,
Some
yeah.
phenomenon explaining that.
Huh.
That's just,
Well, oftentimes there is a real wind situation right before rainfall. So it could have been that there was a high wind that just gave a higher amplitude kind of noise pattern, but no other explanation for you. Sorry. Yeah.
John, I have a question related to your more general remarks where you say seek for a question that matters.
Uh-huh.
And I would agree to that. On the other hand, I wonder whether this is really how the science community works. I often have the impression that questions that are fashionable, or let's say themes that are fashionable, it's much easier to build, let's say, a starting career on than things that really matter.
Well, and that's okay. So Olaf's point is that there's the funding world often will have developed a set of directions that they say these are things that we find important questions, important opportunities. They'll put dedicated funds to particular areas. Interestingly, one thing to watch out for is that it's like fishing. The National Science Foundation will take, in our world, the U.S., they'll put $50 million on a little hook and say, we want you to study roots, okay? And then everyone, and those are the most highly sought after dollars. If you go to the generic call for proposals, oftentimes the competition is much less in the unsolicited, non-fashionable. I think that we have to have confidence that the panels that are operating in all of our countries are populated with people who are quite sensitive to doing good science. They are not fashion contests. So I think these panelists and the conversations are quite rich, typically 20 scientists in a room. And so I personally would say I would never use that as a fashion or perceived community support, blah, blah, blah. Sorry. That's not, I don't think that's a recipe for being successful in the long term. So I personally will put my confidence in the panel. I'll say I'm going to do my job of writing a really good proposal that explains why I'm excited. And then I'm going to trust the panel. And my experience has been quite positive. And I personally, at some times in my careers, there have been some, kind of these opportunities and things are a little fashionable. I've applied for money. And it's often been disappointing to me when I get the money. And it's like, I'm not really interested in this. And then I'll often find something that's worthwhile out of that domain. But I far prefer to chase those things which I'm interested in. And then the second piece of that is that, as I mentioned, you get the funding, and of course this is being videotaped for all posterity, but forget about what you said you do in the proposal. Basically, you've got to choose the best opportunity, and so oftentimes I'll deviate from what I've said I'd do because through the course of preparing and doing the work, you find an opportunity, and so and we often talk to the program managers to make sure they're on board. But I think that these proposals and we have to always be mindful of opportunity.